Hi everyone, and welcome back to this video on the binomial theorem. Today, we're going to be taking a look at binomial coefficients, factorials, Pascal's triangle, a cool way to derive the sum of squares formula, and then we're going to see a nice proof of the binomial theorem with a fun example after that as well. So to begin with, in previous videos we looked at induction, and induction allows us to define recursive sequences whose terms depend upon previous ones. So for example, we can define the factorial of a number through the formula n factorial is equal to n times n minus 1 factorial, and also 0 factorial is equal to 1. So in other words, the factorial is equal to the product of all positive integers less than or equal to n. So for example, 6 factorial is 6 times 5 times 4 times 3 times 2 times 1, which is just equal to 720. Let's now see a fun example of how we can use our new definition of factorial to solve a challenging problem. So in this problem, I want to prove that 1 times 1 factorial plus 2 times 2 factorial plus 3 times 3 factorial plus all the way up to n times n factorial is equal to n plus 1 factorial minus 1. So we can observe that in general, each term of the sum is equal to k times k factorial, which is equal to k plus 1 minus 1 times k factorial, which is equal to k plus 1 times k factorial minus k factorial, which is equal to k plus 1 factorial minus k factorial there. So, therefore, the terms in the sum telescope, and we have that 1 times 1 factorial is just 2 factorial minus 1 factorial. 2 times 2 factorial is 3 factorial minus 2 factorial. All the way up to n times n factorial is n plus 1 factorial minus n factorial. And notice that now the 2 factorials here are going to cancel. So are the 3 factorials. All the way up to the n factorials are going to cancel here. And we're just left off with n plus 1 factorial minus 1, which is exactly what we wanted. We're now going to take a look at the definition of binomial coefficients, which we can define in terms of factorials as n choose k is equal to n factorial divided by k factorial times n minus k factorial. So intuitively, a binomial coefficient is a number of ways to choose k people out of n to be on a committee if we do not care about the order in which these people are selected. So for example, 4 choose 2 is equal to 4 factorial divided by 2 factorial times 2 factorial, which is 24 divided by 2 times 2, or that's just equal to 6. And then Pascal's triangle is an array of binomial coefficients. So the rows are numbered beginning with 0, so the entry in the nth row and kth column is n choose k. And we can see the first 4 rows, or first 5 rows of Pascal's triangle here. We start with row 0, and that's 0 choose 0. Then we have 1 choose 0 and 1 choose 1. And then we have 2 choose 0, 2 choose 1, 2 choose 2, and so forth. And we get this nice looking triangle. And you might notice a cool fact here, which is if you take the two numbers above a given number, the two of them sum to the number below it. So for instance, 1 plus 3 is equal to 4. 3 plus 3 is equal to 6. 2 plus 1 is equal to 3, and so forth. So Pascal's identity says that n choose k, so the entry in the nth row and kth column is equal to n minus 1 choose k minus 1 plus n minus 1 choose k. So it's equal to the two terms directly above it. Let's see a cool proof of Pascal's identity now. So Pascal's identity again is written on the screen, and for this we're going to use the combinatorial definition of factorials. So consider a set of numbers 1 through n. And the question which I want to answer is how many ways can I choose k numbers to put boxes around? And I propose that there are 2 ways to count this. By definition of binomial coefficients, this is just n choose k, because I have n numbers and I need to choose k of them. However, another way is consider specifically the number 1. If 1 is boxed, then I have k minus 1 numbers to box out of the remaining n minus 1 numbers. And this can be done in n minus 1 choose k minus 1 ways. Alternatively, if 1 is not boxed, then I have to choose k numbers to box out of the remaining n minus 1 numbers, and this can be done in n minus 1 choose k ways. And in total, there are n minus 1 choose k minus 1 plus n minus 1 choose k ways. And because these two things count the same exact thing here, we see that the two terms must be the same. So we've now proven Pascal's identity. If there's another proof that you like of Pascal's identity, be sure to leave it in the comment below. There's also an algebraic proof of Pascal's identity that is included within my textbook. So we're now going to see a cool way to prove the sum of squares formula, which is that 1 squared plus 2 squared plus all the way up to n squared is equal to n times n plus 1 times 2n plus 1 divided by 6. So we begin by observing the fact that 1 plus 2 plus 3 plus all the way up to plus n is equal to n times n plus 1 divided by 2. Furthermore, we're now going to prove that 2 choose 2 plus 3 choose plus all the way up to n choose 2 is equal to n plus 1 choose 3 for n is greater than or equal to 2. And to prove this, we're going to use our best friend induction. So when n is equal to 2, we see that 2 choose 2 is equal to 3 choose 3, so that works. And we now assume the identity holds for n is equal to k. So we have that 2 choose 2 plus 3 choose 2 plus all the way up to k choose 2 is equal to k plus 1 choose 3. Now adding the next binomial to both sides of our hypothesis gives us, we now have 2 choose 2 plus all the way up to k choose 2, and we add k plus 1 choose 2, and what we're going to get is k plus 1 choose 3 plus k plus 1 choose 2, which is just equal to k plus 2 choose 3 using Pascal's identity now. Awesome. So we've now seen a proof of this fact, and we're now going to use these two facts that we've seen to prove the sum of squares formula. So therefore, this identity holds by induction. So we can observe that k squared is equal to 2 times k choose 2 plus k. So therefore, if we sum up the first n squares, we're going to get that it's equivalent to the sum over here, the sum of k equals 1 to n of 2 times k choose 2 plus k. We can now rewrite this summation because we have 2 times the sum of k choose 2, which is just going to be equal to n plus 1 choose 3, plus the sum of the first n numbers, which is going to be n plus 1 choose 2. And we can now rewrite this as 2 times n plus 1 times n minus 1 divided by 6, by definition of factorials and binomial coefficients. And then we can rewrite the other term as n plus 1 times n divided by 2, as we saw before. Now, when we factor out n times n plus 1 divided by 2, and we do a little bit of algebra, we get that this is equal to n times n plus 1 times 2n plus 1 divided by 6. And we've proven our sum of squares formula. We're now going to see the binomial theorem. And we can observe the following expansions are the coefficients in Pascal's triangle. So x plus 1 to the first power, x plus y to the first power is equal to x plus y. X plus y squared is equal to x squared plus 2xy plus y squared. X plus y cubed is equal to x cubed plus 3x squared y plus 3xy squared plus y cubed, and so forth. And these coefficients, 1, 1, 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1, are all the coefficients in Pascal's triangle. And the binomial theorem states exactly that. The x plus y to the nth power, the coefficient of the y to the k term is just going to be n choose k. And we're going to see an intuitive proof of this. So in the expansion of x plus y to the n, which is just x plus y multiplied by itself n times, to get the coefficient of x to the n minus k times y to the k, we have to choose k out of the n factors to be y. However, by definition of binomial coefficients, the number of ways to accomplish this is exactly n choose k. Hence, this is the coefficient in the binomial theorem here. There's also an induction proof of the binomial theorem that you will see in the accompanying textbook. And now we're finally going to use this to prove a very tricky fact about number theory. So we want to prove that if n is a positive integer, that this expression here is always an integer. And let's dive in. So when n is equal to 1, we're going to use induction. So when n is equal to 1, which we prove is the base case, we have 1/5 plus 1/2 plus 1/3 minus 1/30 is equal to 1, which is an integer. And we now assume that s, which we define as k to the 5th divided by 5, plus k to the 4th divided by 2, plus k cubed divided by 3, minus k divided by 30, is an integer for arbitrary k. And we now want to expand the expression for n is equal to k plus 1 using the binomial theorem. And we start with expanding k plus 1 to the 5th power. And when we do that, we get k to the 5th plus 5k to the 4th plus 10k cubed plus 10k squared plus 5k plus 1 divided by 5. And now we're going to expand k plus 1 to the 4th power and k plus 1 cubed. And we're going to get for k plus 1 to the 4th power, we get k to the 4th plus 4k cubed and so forth. And for k plus 1 cubed, we get this expression here. And we can now do a whole bunch of algebraic manipulations, and we see that this expression is actually equivalent to s plus a whole bunch of terms here that are all in terms of k, but because k is an integer, we know that all of these terms will be integers as well. So therefore, this is an integer by the induction hypothesis, and we prove that this tricky expression is always going to be an integer.